Ever boil water on a mountain and notice it boils colder? That's saturation pressure in action. Quiet, invisible, and absolutely running half of modern industry. Here's the hook. Every liquid has a point where it's perfectly on the edge of becoming vapor. At that point, the pressure of its vapor equals the pressure sitting on top of it. That pressure is the saturation pressure, and it depends on temperature. Raise the temperature, the saturation pressure climbs. Lower it, it drops. If the surrounding pressure matches the saturation pressure, boom, you're on the knife's edge. Any nudge in liquid flashes to vapor, or vapor condenses to liquid. Let me explain it simply. Picture a sealed container with water. Some molecules escape the surface and become vapor. Some vapor molecules dive back into the liquid. At a certain temperature, these two flows balance. The vapor pressing on the walls? That's the saturation pressure. Heated, molecules move faster, more escape, and the saturation pressure rises. That's why at sea level, water boils at 100 CUI, because the saturation pressure of water equals atmospheric pressure. On a mountain, the air presses less, so the match happens earlier, and water boils at a lower temperature. Now, why do industrialists care? Because controlling saturation pressure is the steering wheel for phase change. Boilers and steam turbines. Engineers pick pressure to set steam temperature. Higher saturation pressure means hotter steam, better turbine efficiency, up to materials and safety limits. Refrigeration and heat pumps. Compressors raise refrigerant pressure above its saturation point to condense it and dump heat. Then expansion drops pressure below saturation to evaporate and absorb heat. The whole cold chain lives on these curves. Distillation. Columns use pressure to shift boiling points. Lower column pressure lowers saturation pressures, separating heat-sensitive chemicals gently. Vacuum drying and freeze drying. By pulling vacuum, saturation pressure falls, so water evaporates or sublimates at low temperatures. Perfect for pharmaceuticals and food. Storage tanks and safety. Relief valves and blanketing gases are set around expected saturation pressures to prevent boiling, collapse, or overpressure. How do they actually work with it day to day? Use property charts and equations like Antoine or Clausius-Clapeyron to map saturation pressure versus temperature for each fluid. Instrument everything: pressure and temperature sensors, saturated steam tables on the HMI, and alarms when processes hit the wet edge. Control loops, compressors, valves, and heaters modulate to stay just above or below saturation depending on the step. Pinch analysis and optimization. Choose pressures that trade off energy use, equipment cost, and product quality. Materials and safety. Select gaskets, alloys, and relief devices rated for the maximum credible saturation pressure at the hottest credible temperature. Seasonal and altitude adjustments. Same recipe, different site pressure. Retune set points at high altitudes or weather swings. Data and AI. Digital twins simulate saturation behavior, so operators predict when a column will flood, a chiller will short cycle, or steam goes wet and choose blades. A quick mental model to apply. 1. Pick your target phase change. 1. Look up the fluid saturation pressure at your desired temperature. 1. Make the system pressure slightly above that to condense, or slightly below to boil, evaporate. 1. Add control and safety margin. Try this at home, not with pressure vessels, but you can see the idea by boiling water under a lid, then cracking it open. The pressure drops and it flares. Same physics, tiny stakes. Saturation pressure isn't trivia. It's the dial that turns energy into work, cold into comfort, and mixtures into pure products. Learn to read it, and you can steer almost any thermal process with confidence.